Okay, we have integral number 6 for this video. If you want to give it a try, go ahead and pause the video, and I'll be right back. So this particular integral involves a rational function for the integrand. Degree of the numerator is less than the degree of the denominator. Now you could go ahead and break this down using partial fraction decomposition into two integrals. And one is very easy to integrate. The other one you'd have to use a trig substitution. So I'm just going to go ahead and use a trig substitution to start off with to avoid the partial fractions. So I'm going to let me form my triangle first here. So I'm going to make this angle theta here, this right triangle. There's three main techniques for use for trig substitutions, one involving the sine, one the secant, and one involving the tangent. I'm going to use the tangent based on what I have here. Let this side equal to x, this side equal to 1. So by the Pythagorean theorem, then I know that the hypotenuse should be square root of x squared plus 1. So now I need to replace these x terms here using this substitution here. I'm going to let tangent of theta equal to opposite over the adjacent. That's x over 1. So that'll just be an x. So I need substitutions for x squared. So from this substitution here, I square both sides. I get an x squared is equal to tangent squared theta. So the x squared will be replaced by tangent squared theta. Now for the dx, again using this tangent of theta equal to x, derivative of the right side, that's a dx. And for the tangent, that'll be secant squared theta d theta. And then for the denominator, I've got x squared plus 1, and that's quantity squared. So again, I'm going to use the substitution for x equal to tangent theta. So right here I have the x, put tangent in there. So that's going to give me tangent squared theta plus 1. And then that'll be squared. So I got x squared plus 1 quantity squared in the denominator, replacing the x by tangent squared. I get this right here. But tangent squared theta plus 1, that's one of your basic trig identities. That's secant squared theta. But that's squared. So that gives me secant to the 4th theta. So now we're kind of set here. Come over here, equals, so we got the integral of x squared. That's going to be a tangent squared theta. And then the dx can be replaced by secant squared theta. That's a d theta now. And then in the denominator, that's secant. The x squared plus 1 quantity squared, as we saw, is now secant to the 4th theta. So these two squared can be cancelled. That'll make this a 2 now. So this reduces down to tangent squared theta over secant squared theta d theta. But again, just to save some steps here, this is secant squared is 1 over cosine squared. Cosine and secant are reciprocal, so I can replace the secant squared by cosine squared theta. And then multiplying the numerator and denominator by cosine squared. Remember, tangent squared theta is sine over cosine, sine squared over cosine. So multiplying numerator and denominator by cosine squared theta, and down here cosine squared theta. So for the tangent squared theta, the cosine squared cancels. That leaves me just with sine squared. In the denominator, the cosine squared canceled to 1. So all I have left then is the integral of sine squared d theta. Even power on both the sine and the cosine. Cosine is to the 0 power. So here I use one of these half angle or double angle identities, depending on what perspective you look at these at. So sine squared is an identity for sine squared. It can be replaced by 1 minus cosine theta. Actually, it's cosine 2 theta. So that's a lot easier to integrate now. Integrate the 1 with respect to theta. Again, it up into two integrals here. Integral of 1 with respect to theta is theta. And actually this is over 2 here. This is over 2. This is over theta over 2. And the antiderivative of cosine is sine. But because we have the negative there, bring down the negative, and we get sine 2 theta. And that's over 2 also, but then you have that extra 2 here from the 2 theta. Take rid of that as 2, so this actually gives me another factor in the bottom of, becomes a 4. Then my constant of integration. So we continue then. At theta over 2. And then the sine 2 theta, there's another identity for that one. That can be replaced by 2 sine theta. Cosine theta. And then you can reduce there. 2 and the 4 can be reduced down. So this will be a minus sine theta, cosine theta. And again, the 2 and the 4 reduce down to 2. So you got this over 2 plus the constant of integration. And we're pretty much finished using the variable theta, but we have to go back to the original variable. So all we have to do is convert this back to x. So for theta, using this substitution here, taking tangent inverse of both sides, we get theta is equal to arc tangent, or I can just say tangent inverse here, arc tangent or tangent inverse of x. So this is equal then tangent inverse of x all over 2. So that could be tangent inverse or arc tangent. And then it's minus. So we have sine theta, cosine theta. So let's look at the triangle. For sine of theta, that's x over the square root of x squared plus 1. And then cosine is adjacent over the hypotenuse. So sine was opposite over the hypotenuse. Cosine is adjacent over the hypotenuse. So that's for the cosine over here in this expression here. That's 1 over the square root of x squared plus 1. Again, that exponent there, x squared plus 1. So this could give me then, going from here to the next step here, got the 2 there, I'll just put a 1/2 in front here like this. And then what I got for sine and cosine, which is up here, multiply. So it's x times 1 is x. And that's over radical x squared plus 1 times radical x squared plus 1. Just gives me the square root of x squared plus 1 squared, which just gives me x squared plus 1. Plus the constant of integration. So we get then for the final answer here, tangent inverse of x, or you can write that as arctangent of x over 2 minus 1/2 the quantity of x over, and that's x squared plus 1 plus the constant of integration. Thanks for watching. We'll see you next time.